Very good morning, Professor Annapurni. Good morning and a very warm welcome, students and teachers of schools. Today we have Professor Annapurni, Director, Indian Institute of Astrophysics, Bangalore, with us to deliver sixth and last lecture of the science series. I am Devesh Avasthi, Dean R&D at University of Petroleum and Energy Studies. Let me begin with a short background of the lecture series. We at UPES initiated a science series consisting of 6 lectures by renowned scientists of India and abroad, especially for school students and teachers, in association with Institute of Physics UK, Indian Physics Association, and Indian Association of Physics Teachers. There has been participation of a large number of students and teachers in the lecture series. The lecture series is giving you a glimpse of different aspects of science, challenging problems, as well as the experimental infrastructure in India and abroad to pursue an exciting career in science. First lecture of the series was by Dr. Shashank, Director, Institute of Plasma Research, Ahmedabad, was on plasma and its technological applications. Second lecture was by Professor Rao, Director, Indian Institute of Technology, Delhi, on nanoelectronics, which revealed a strong connection between physics and engineering and nanoelectronics. The third lecture of the series was by Professor Samit Kere, former director of SN Bose Center, Calcutta, on wonderful world of materials. Fourth lecture of the series was by Dr. Archana Sharma on unlocking the secret of universe. Fifth lecture was by Dr. Amit Roy, ex-director, Inter-University Accelerator Center, Delhi, on accelerators in science and society. Today is the sixth and the last lecture of the series by Professor Annapurni on why should we study stars. Topic of today's lecture is very attractive and make us curious. Let me describe UPS in a very brief. UPS is a research and innovation driven university where students get a chance to learn with the leaders in respective field of science and engineering. The university provides funds to faculty under seed grant scheme and to students under Shodh grant scheme to pursue experiments on their innovative ideas in the focus research areas of energy, water and environment, health, diagnostics and therapeutics. The university has agreements with hospitals and industries for applied and translational research. Apart from this, the basic and fundamental research is also encouraged at university. I am thankful to Professor Annapurni for sparing her valuable time for the lecture to students and lectures. For your information, there will be quiz at the end of lecture series on 7th August based on the questions from lectures and school level science knowledge. 2 quizzes are planned separately for school students and teachers. The students and teachers attending the lectures are welcome to participate in the quiz. The prizes is sponsored by Indian Physics Association and Institute of Physics UK will be given to the winners. Now, before requesting Professor Annapurni to deliver her lecture, I will give a brief introduction about her. Professor Annapurni Subramaniam is the director of the Indian Institute of Astrophysics, Bangalore. She has about 3 decades of research experience and has published about 150 research publications in topics such as star clusters, stellar populations, galaxies, and ultraviolet astronomy. She has guided large number of students and have 10 completed PhDs. She is currently the chief editor of the Journal of Astrophysics and Astronomy, jointly published by Indian Academy of Sciences and Astronomical Society of India. She is also a scientific editor of Research in Astronomy and Astrophysics published by the Chinese Academy of Sciences. She was involved in major projects like UV imaging telescope on board India's first space observatory, AstroSat. She was heading the Indian team of the observatory software, completed the delivery common software in 2019 for 30-meter telescope, which is being built by an international consortium with India as a partner. She is the principal investigator of proposed next generation UV optical space telescope funded by ISRO. She has several awards and fellowships to her credit. Some of these are Fellow of Indian Academy of Sciences, Fellow of National Academy of Sciences, Life Member of International Astronomical Union and Astronomical Society of India, Kavli Frontiers of Science Alumni instituted by Kavli Foundation and National Academy of Sciences USA, recipient of C.V. Raman Young Scientist Award for Physical Sciences from Karnataka government for the year 2018, recipient of SERB Power Fellowship 2021, and many more. So with this short introduction, I request Professor Annapurni to deliver her lecture. Over to Professor Annapurni.
Yeah, thank you. Thank you, everyone, and good morning, everyone. Thank you, Professor Avasti, for giving me an opportunity to talk to the students and share my passion for doing what I'm doing, and which is basically looking at stars and studying them. And can I go ahead and share my screen and present my talk?
Please do so. Yeah.
Yeah. I hope you all can see my screen and hear me well.
Yes. Yes.
I just will try to this is blocking right onto the, is it anything blocking my slide?
No. I
Okay, all
think
right, then that's fine. So I'm talking to you today about stars, and I thought I'll coin this topic as the why should we study stars. So astronomy and astrophysics is about study of space and everything in out in space. But what is there out in space? Mostly it is stars. But then stars get grouped together to form galaxies, etc. There is a vast amount of space between the stars. There's a vast amount of space between the galaxies. But in general, when we look at sky and say something, we two things come to our mind. One is planets, which is there in the solar system, and stars. So mostly it's dominated by stars. And why I thought one would go out and look at so many stars in the sky, and the nearest star we have is the sun. So many of out them, so many are there out there. So why should we study all of them? Can we just study our sun and say that's all? That's the closest one we have, and we'll study it in grand detail, and that's the end of it. We know the entire universe. So how does that work? Is it that enough? No. So I would like to tell you what is it all about, and in the broader context, how do stars affect our daily life, not in terms of but in terms of guiding our day-to-day activities in terms of science. So that is what I wanted to convey today. So this is one of the pictures taken from the of the sky. The pictures. This is from the southern hemisphere. But I would like to point out that there are various objects on this picture, which suggest that there are you can see there are stars which are scattered, and you can see a band of sky where the density of stars are more, and then you have a patch of I mean some kind of a cloudy or patchy thing here, which we know that it is a galaxy. It is one of the nearby galaxies. Another thing here is also patchy but not very clear in this picture, which is also another galaxy. You need better, bigger telescopes, or with good power to resolve the stars in them. But we know that these two are galaxies, and this is the closest one here, which is the comet. So just give me a second. This is kind of bugging me. Let me just get out of the.
Yeah. Okay. You are not able to move the slide, or
No. The
fine. Fine.
panel which is shown here is irritating me.
Okay. Okay. Okay.
I'll just compress it so that it is.
आपका
Yeah,
शायद
yeah, I have done it. I've done it. Yes.
you can maximize this scene. I think this.
Yeah. I've done it. Yeah.
Yeah.
Sorry.
Okay. Okay.
Yeah, so one of the fascinating things which we have seen, a lot of pretty pictures which are catching our attention these days are this wonderful astrophotography and fascinating pictures of the night sky. And I would like to point out to you that the factor which actually triggered my joining astronomy and astrophysics is the very nice, beautiful night sky filled with stars when I used to be watching when I was a kid. So I grew up in an interior part. I'm in Kerala, but in an interior part, it is actually quite dark. And of course, we used to have a lot of power cuts in summer. So you come out of the house and look at the sky. You can't sit in the house; it's very hot. And you come out and you look at the sky and then you see a lot of bright stars out there, and then you start wondering why are they there, and are they the patterns remain the same throughout the year, or do they change? So you start wondering more about things, and a comet appears, and then it triggers all your interest in why is it coming, why is it coming once in a while, where does it go back to? So all these questions started coming to my mind, and then I realized that it is my calling, and I wanted to take up astronomy and astrophysics to study further. But these days, students or children or families who live in cities which are polluted with the lights, you can't see anything in the sky except a few bright stars or planets. But if you go to places where they are dark in the evening, there are no lights to pollute the sky, you get brilliant pictures, brilliant views of the sky. And one such place, this is in the Himalayas in Hanle, it's 4,500 meters above sea level. And this is the site, and this is one of the pictures taken. It's a long shot picture, of course, a long exposure picture of this is a Milky Way right above the telescope. So this image the picture is taken by Dorje Angchuk. He is the engineer in charge of our observatory there, and this is his Twitter handle. So you can see the beautiful pictures, and people the digital transformation of the photography has resulted in all these beautiful pictures being taken and produced. So this is not possible from any odd place. It is possible only from places where they are fit to be observatories, because we need the very less light pollution. So observatories are set up in places where the light pollution is less, so that you can see stars. Now coming back to our picture of our idea of okay, this is another picture taken from the thing. This is about one of the comets which appeared recently last year, Neowise, and this is one of the award-winning pictures. This is actually the comet is here, and you can see a huge tail, and this is another outgassing coming out of the comet, and in the photography you can see it with a different color. So this is also from our Indian Astronomical Observatory, Hanle. Again, this by Angchuk. Now, I also suggested that uh, stars do help in our daily day-to-day life. Now, how does that work? Now, also that looking at the sky, astronomy is one of the ancient science, right? Humankind has been pursuing the science for ever since we know. So why is that, and why is that is still an important science when you started looking at the sky for so many years, right? So why did we start looking at the sky? For two reasons. One, we need to know the time. There was no clock, there was nothing. So you need to know what time of the day it is, how many more time I have before it becomes dark, or if it is dark, how much more time I have both before it becomes day. So these kind of estimations you need to do. And how do you do? In the daytime, of course, you can look at the shadow and things like that, and then estimate. But in the night, you need to know the constellations, you need to know which stars rise at what time and which part of the year. So that is how the calendars are made and seasons are ascribed, etc. So you study over a few years, you can see the pattern and put it together, and then make sure that it repeats, and then you follow that. So that is how it is done. So if you look back and see how people survived, looking at the sky and understanding the stars were one of the essential requirements for staying alive. So it is one of the life skills required then. But now, is it required? Of course, you look at the sky and say outside and say, oh, it's already evening or already morning, etc. But beyond that, it doesn't work as of now. Now, what else was stars used for? Navigation. if you want to go from one place to the other, you need to know the direction. You need to know you need to go northward, you need to go eastward or westward or whatever. So during the daytime, you can use sun and then you can understand which direction it is. But during the night, it is just not possible. In the case of navigation, if you're in the sea and night you want to navigate, you have no idea. You need to look at the stars. So the two galaxies which I showed in the beginning, which were looking like patchy things, are actually named after Magellan, the Voyager, and they're called Magellanic Clouds. So you use them for navigation because it is prominently seen in the south sky for very long period of the year. So or most of the year it is seen. So use that for navigation. So navigational purposes and finding directions, the stars played a major role in the past. Now, what is the status now? So, as I said, timekeeping used to be one of the requirements, now it is not. But what about directions? Do we use stars for directions now? I think most of you will say no, we don't. So even if you want to go from one place to the other, I want to go to from here to another place in Bangalore, or I'm driving down somewhere. What do? Google Maps, you look down. Instead of looking up, you look down, right? So how does the mapping work? Have you asked yourself that question? So mapping works by a set of satellites. It's a GPS tracking, right? So you have positions, you have to position yourself, and then you have a map, and then within the map, you have to locate yourself. Now, location is what I'm talking about. I'm not talking about creating a map. I'm talking about locating yourself. So if you're driving down, you know which way direction you're going. So this is a GPS tracking. Now, how does the GPS tracking happen? You have a set of satellites out there, which is like a cluster around the Earth and which they're moving. They're not stationary. They can't be stationary, otherwise they will just fall back into the Earth. So they have to move. They're on orbits. The line shown here are on orbits. Now, they at least two satellites can track you and say that with respect to both these satellites, the position of that gadget where you hold, where the GPS tracker is out there. So that's a technology. That technology is helping you to track you down to a very accurate level. Now, how do they know where they are? They can track with respect to themselves, but you have to be pointed down to exact position on the earth, location on the earth. It's not a relative positioning, it's an absolute positioning. In order for the absolute positioning, the satellites needs to know where they are. Are they stationary? They're not. They're moving. Is the earth stationary for that matter? No, it's also rotating. It's also moving with respect to sun. Is the sun stationary? No, sun is also not stationary. Where is it going? It is going around the galaxy. Now, in very, very large time scales, the sun goes around the galaxy happens. But overall, when you look at certain time scale, there are certain corrections to be applied, which acts on your precision. So in effect, what happens is all these are moving. There is no absolute frame of reference for pinning it down. Now, what is your absolute frame of reference then? You need one absolute frame of reference which doesn't move with respect to us, or the movement is completely negligible. So in the earlier years, one used to have a fixed framework, which is the stars, faraway stars. So at least 30, 40 years back, we used to look at the nearby stars for the as the framework, and then estimate this kind of locations. But now we know that even the nearby stars move, just like the sun moving around the galaxy, these nearby stars are also move. That is also not providing the required accuracy. So what is actually shown is the used is a set of quasars, um, which are very, very far away. So these are provided by astronomers, and as it's mentioned here, these 212 GPS quasars are used as frameworks because you know their positions absolutely well. And these are used as the absolute framework within which we can identify the location of everything. So what are quasars? They're astronomical objects, but they are nothing but huge black holes which are powering the central engines of certain galaxies. You can't see the galaxy as such, but you can see the central engine as a point source like a star. So these are what is guiding us. These are the quasars are what is the providing the framework for our day-to-day navigation through GPS. Now, so what is the bottom line? The bottom line is that the stars or the celestial objects are still guiding us or helping us on our day-to-day life, though we do not look at them by ourselves, but we use gadgets and technology to look at them. So I would say that stars are still relevant. Stars, in the sense that the central engines of these quasars are, in fact, supermassive black holes, and they start from the feed small black holes and merge and then become it's a huge black hole. So we still do not know how these supermassive black holes are formed, but they are the ones who are responsible for this GPS and in the quasars, and then in turn helping us to for our GPS positioning. So the other important thing is this is the technology, a combination of technology and astronomy together. And there are a lot of other technology driven, astronomy driven technology which help us to look at various things. So many of them are put together by International Astronomical Union. There are a lot of technology transfer, development of cameras. Actually, the cameras you see used in our cell phones were the charge coupled devices were actually a device for astronomy purposes. They were very, very difficult to get, and all kinds of restrictions were there for technology transfer, etc. But over about 2 to 3 decades, it became very cheap, and it could be large scale production could be done, and that's now where we are. And mobile communication from radio astronomy, from X-ray astronomy, which is used in the airport scanners, image processing, etc., are all transfers driven by technology transfers, technology driven by astronomy. And I still continue. I'll come to later my slides how astronomy drives technology, and that actually transfers certain kind of applications to our day-to-day life. So though it takes about 2 to 3 decades, eventually that is what happens in the case of astronomy. So these are some of the examples. Now coming back to, again, why should we study stars? Um, this is a periodic table, right? So I don't think any of you require introduction to the elements which are listed out by Mendeleev. This is about more than 150 years old. And of course, when it was put together 150 years back, many elements were not there, and it grew and grew, and this is the kind of state it is in. And you study in terms of various types of, like, the elements are grouped, alkali elements and inert gases, etc. And then various types of things are grouped together based on their properties, and the students study it in a slightly different way. Now, the question I'm asking is, how are these elements produced? Now, you know that, most of you know that they are all called, as we know, the atoms, the nuclei is positively charged, and you have negative charged electrons in a cloud form around it, and we can actually quantize in terms of shells, etc. Now, how do you make different types of elements, right? We know that we understand, or from our observations of the cosmic microwave background radiation, we understand that there was a big bang, and in that time there was a energy, and it is a soup of everything, particles and energy, etc., together, and there was a matter and energy decoupling, and the matter started cooling down, and then they started producing elements. So you, in that form, you can only produce the very light elements like the hydrogen and helium, nothing more than that, a small fraction of a little bit more, but not much. But how did you create the rest of it? Now, that is where the stars step in, because the very first cloud, when you actually cool down, you form stars, and the interiors of stars become very hot, and they start fusing. That temperature, they are the actual live nuclear reactors out there, including our sun, and where the light elements fuse to become heavier elements. And not all stars can produce this, but some the depending upon the mass, they make all these elements within them. So here is the color coded one. So what is shown here is that this the elements which has got this particular band of green are produced in large stars. And in the case of this yellow, chromium yellow, banded elements are produced in small stars as well. So you have a combination of certain elements produced in large as well as small stars, but some are produced only in large stars like these, and some are produced mostly in the yellow ones. So mostly these are only coming from yellow smaller stars. And you also have a lot of elements coming from supernovae. I'll come to, most of you would have known what supernovae are, but I'll come to it in a minute. So the supernovae produce most of it, and then you have also, I should say that some of the elements produced in certain large stars and ejecta, where you have mostly a lot of neutrons available for enriching the nuclei. So they produce the bigger, the heavier elements here. And then only the last ones are from man-made, and they are mostly very unstable. So, looking at this astronomer pure astrophysics point of view, all the elements are, you need stars to make elements, and that is one condition. But we also can use this kind of barcode which is provided here to decipher. If you see a barcode somewhere, you can actually see that, oh, okay, this is what the elements are present here. Now that would mean that some kind of, these kind of stars polluted this place. So it gives you a signature of what happened in that place before time. So it gives you a history of what happened in our neighborhood or in that neighborhood before that particular star was born. So it gives you a chemical signature. So moving to the next slide, I can explain you here. So what happens is you have a nebula where you have a huge amount of cloud of hydrogen, which actually falls under its own gravity to form star. And then the star evolves like a sun, which is called a main sequence star, and then it becomes a red giant, and then it dies either mostly as a planetary nebula in the case of low mass stars, and in the high mass stars it dies as a supernovae. Now the difference is, in the main sequence where it is shown is mostly like a sun, where the interior part is converting hydrogen to helium. So you are making the interior of the star more and more of helium, and which is actually originally was more full of hydrogen. So the helium content starts increasing, and when the helium kind of core collapses, the star expands and then become a red giant. Now that process of helium converting into carbon and etc. will start later, and then when the core finally collapses is when the supernova happens. Now the core is massive, and massive enough in the case of massive stars, and the ejecta is very massive, and a very powerful ejection is what you see in the supernova, with the remnant as a neutron star or a black hole. So again, the black hole is a remnant of a stellar evolution, and you get an ejecta, which is a pollutant which is getting into the outside in between the stars. In the case of sun-like stars, you have a planetary nebulae, but this is a slow ejection of matter. Of course, the envelope is small, so you will have a small amount of matter getting mixed up, but there is amount of matter mixed up. So what I mean to say is that if you started with a pristine nebula and you go through this particular process, you end up throwing more and more evolved material into the medium. So stars are pollutants. They cook elements and pollute. So that's what happens here. It is from this thing. That is the reason why we say that this is taken from Daedalus, the American Academy of Arts and Sciences, which actually says that this is the kind of elements we all have. So we are all made of stardust. You would have heard that, why we are made of stardust, right? So this is actually what it means. All the elements which we carry are cooked up somewhere, sometime in the stars. Now, how does that happen? So as I mentioned, astronomers use something called we see in any other form of physics, or in terms of technology, etc., development, or engineering, physics, etc., you can go and touch things, break it, mold it, heat it, whatever you want, you can do it, react with another reagents, and find out what it is about. In astronomy, if you want to study stars, you can't go near it, it'll burn you off. So you can't even put a probe. Right now you have a probe near the sun. It cannot cross a certain limit because it can burn off. So you can't get material. The only thing right now we are getting material is that two spacecraft which has gone to asteroid and brought back some material. And we hope we can get material from our own neighborhood, right? Beyond that, we can't get material. These are all very rare cases, or when a meteorite falls onto the earth. Other than that, we cannot touch any of the material. They are all plasma, boiling plasma, huge hot plasma. So what do? We can only get the energy out of them, analyze the energy, and study what they are. Now, this is some physics diagrams which we use to understand what is the energy, what is the temperature, etc. I don't want to go into in detail. If anybody has questions, I'll come back to it. But this is a bit of a technical thing. But then the y-axis shown here is the energy, total energy emitted, and this is the temperature. So these are two broad uh, quantities which we can measure and group them. Just like in any sciences, in biology or chemistry, astronomers are also group things. They classify stars, they classify galaxies, and say that these are the type of stars, and they name them. So what happens is, why do you have classification? When you start classifying, then you say, oh, this is a group. Even in viruses, you have a group. This is a group, but then they have small changes, etc. Right? That's how we have coronavirus classification among viruses itself. So just like that, it's classification, and you have certain types of stars which have these properties. So if you find another one which has got similar property, you classify them. This helps us in classifying stars. So this is called a fundamental Escher diagrams, the Hertzsprung-Russell diagram, which is one of the fundamental diagrams used in astronomy. Going forward, so what happens in advanced evolution is that, like the sun, like stars, or young stars, which can, when they form, they're mostly of hydrogen. You can see this one color. Now, this is the situation where sun is in, where the core is more and more of helium, and the outside is more and more of, mostly of hydrogen. Now, sun is a very low mass star. When you look at stars which are 20 times, 80 times, etc., more massive than the sun, they go through this evolution very fast and also produce a lot more elements inside. Now, how they produce is that you can see that as and when it ages, you have the core gets more and more into different types of elements. It reaches to a stage where you can see this picture where you can, the innermost core is iron, and then you have magnesium and neon, then silicon, then carbon, then helium, and then finally the outside is like hydrogen. So we call this like an onion skin model. If you cut an onion, you can see the layers and layers, right? So this is like something similar to that. So the innermost part is like iron, and then you can see all these elements as layers. So what happens in a supernova is that this iron core, it cannot fuse any further because of certain restrictions, and which we know in laws of physics. It collapses, and the energy released in the collapse is lifting the entire envelope out, starting from magnesium, neon, etc. Now, this entire envelope lifts, and all these elements get thrown out into the interstellar medium. So that's what happens. And then if there's a spin, then it becomes a spinning black hole, and you have jets, etc. So this is the typical big picture of the supernovae and how they explode and what happens to the remnant. And I should also say that though these layers are shown here, there are a lot of neutron production and certain other types of reactions in nuclear physics can also take place, something called neutron captures, which end up producing all these intermediate elements which are not shown here. So you can ask that, okay, you have shown all these layers, you know specifically these elements, but what about the other elements? Where are they coming from? So they are coming from the intermediate reactions which can take place there. So one can explore and find out. So these are the typical lifetimes if you want to look at, and these are the type of temperatures you're looking at. So if the core temperature is something like a million in terms of sun, and then it becomes much more hotter and hotter when it becomes more and more massive stars. So these are the kinds of temperatures required. These are types of elements reactions which we go through in different stages, and these are different types of elements which are there. So you can see that. And as I mentioned, you also end up having this proton-neutron exchange reactions as well as multiple neutron capture reactions, which produces different types of elements with the Z greater than 28, etc. So what I want to convey is that stars are the actual live nuclear reactors, and they produce all these elements because of this temperature, pressure, and available within the star. So they are responsible for production of all the elements in the universe. Now, what happens? This is something called an ecology takes place because you have mostly atomic hydrogen then they cool down to become molecular hydrogen, and then they collapse to form stars and they die, and they put back the material into the interstellar medium. So it's a cycle turning. So a star gas star cycle. Now, when the cycle turns more, you produce more and more pollutants, more and more elements, and more fraction of certain elements. So if you had only certain types of stars, you will produce only certain types of elements. If you had all sorts of stars, you'll produce all sorts of elements. So that is why I said they live behind a chemical signature. And any cycle turns, you can actually check what is the chemical composition of a particular region of the galaxy or a star which is now born, and you can actually say what kind of stars lived prior to the formation of the star. So even for a sun and the environment of sun when it was born 4.5 billion years ago, we can actually say this would have happened here. Okay, so this is the signature they leave behind. And I also wanted to show one more figure on this. So you also get certain material for processing. The pollutants come from smaller stars, bigger stars, etc. But at the same time, you also block off certain mass which are not available for recycling, which are remnants, white dwarfs, neutron stars, black holes, and certain brown dwarfs which are actually failed stars. So this is the kind of ecosystem which we see anywhere in the universe. Um, Going forward, um, so in any galaxy, actually, this is a galactic structure. Our galaxy, sun is located here. This is the disk of our galaxy as we know it, and this is the bulge. And the bulge has more density of stars. On the other hand, the halo has less density of stars. And this is the disk where we see most of the gas and the young stars are located. Now, there is how do they survive? There's a huge amount of understanding of dynamics involved, because everything moves and they balance the gravity. Otherwise, you can say that the gravity can attract everything, and everything can collapse in no time. So it doesn't collapse. It's like a sun has been at its the same distance for we don't see any trace of it moving away or moving in. So the dynamics plays a huge role. So we understand the dynamics as well. But the stars dynamics, the motion of stars help us to understand the dynamics as well. So how is the moving takes place in our galaxy? We also need to understand the motion of stars. So they give us an understanding of how fast we are expanding or contracting, etc. Same is the case of galaxies, how fast they are moving away. So a dimension of the universe as such, or nearby local bubble or local groups of galaxies, etc., also come from the how the stars move, and that we measure with respect to velocity. Um, okay, so we what do we study? We see history. The formation and evolution of stars help us tell us the history of where we are. We do study through groups of stars called clusters. These kind of clusters are called open clusters, like the Pleiades, the Hyades, if you look at the sky. The globular clusters which are very dense clusters. I think only Omega Sun, which is quite bright, but the rest of them are quite faint, because these are stars which are quite less mass than the sun, but their density is very large, and they're very old systems, and they have preserve the information on how our galaxy formed, etc. And there are associations like this which we see in the Orion complex, which are very, very new. And if you look at an outside galaxy, all these spiral arms are delineated with the new stars. That is, they are very bright and young, and we know that they are groups of stars. And they studying them tell us about the chemistry there, what happened before that, and why they are formed now. So and studying their velocity, etc., tells us the dynamics as well. So what we are looking at is the history of things which has happened before anything which we are studying now. Geography, how they are distributed, location, sizes, and shapes, and they have a bearing on the dynamics as well. Physics, that is where dynamics comes in, and the nuclear and the magnetic field, because the nuclear processes happen in individual stars, and magnetic field happens for individual stars or star forming region, but also for the entire galaxy. You have a magnetic field threading everywhere. So they play a very huge important part. So that is where physics gets connected through these things. And hydrodynamics is also coming in place in terms of material flowing within a star or within a galaxy or within material which is accreting around black holes, etc. Chemistry, you have all sorts of elements, you have formation of molecules in a cooler region. So chemistry is stretched here. Extremely hot regions, just like the interiors of stars. We also have extremely cold regions between the galaxies, between the stars. These cold regions are ideal for forming molecules, complex molecules. So study of these complex molecules are extremely important now, and all the more because we now know about exoplanets and how the planetary formation takes place, and then how complex molecules, do they get destroyed or do they get actually formed on this within the material of this planet. So that is an important thing. And mathematics threading along all this complex equations, complex geometry, etc., play important roles. So all forms of physics contribute to understanding our universe as well as stars and the complex of stars for with clusters and galaxies. Now, how do we get to study them? We know that the atmosphere does not transmit all the wavelengths. So this is the wavelength in the transmittance. So you have maximum transmission around the visible wavelength. Now, as I mentioned, I have not plotted if you plot the light pollution as well, the amount of light you can see along with the pollution, because pollution raises the background, will be only so much. You can't see anything above it. So if you go to ideally a good sites where good locations where you have light pollution is minimal, and also the clouds are not there, and absorbency of the atmosphere is also minimal, you have maximum transmission. So if you want to take collect the light coming from or energy coming from all these sources, you need to locate your instrument which can collect, your camera or any other instrument, in a place where you have maximum transmission. So the atmosphere does not absorb much, and you are able to collect most of the data within your thing, so that you can, because then only you can fainter, right? You can go fainter. Otherwise, you'll be seeing the sky from like this sky from the cities where all the faint stars are completely not seen. So this is the case. But is that all the objects out there emit only in this wavelength? No, they emit in UV and X-ray, etc. But also they emit in the longer wavelength. Some of them are like this window is infrared is available, but you can see that this window where most of the emission coming from the cool a medium between the stars, where the cloud forms and the star formation happens, etc., are not available, and the radio is still available. So some of them are hidden from because of the atmosphere, which is actually protecting us here in the case of ozone, right? So how do we handle that? Do we say that the objects out there emit only in this wavelength? No, we cross over and go to outside atmosphere to collect their to understand how they work. So how do we do it, and what do we do it here? So my institute, which is the Indian Institute of Astrophysics, we have several field stations which are located with telescopes, and our ground-based telescopes are shown here. We have one in the which I already showed you, the Hanley telescope, 2-meter telescope. We also have the study of the sun has been carried out from Kodaikanal using optical observations. We also have to study the sun because the sun emits plasma, and once the plasma leaves the surface of the sun into the medium between the sun and earth, they are plasma which is not visible through normal optical telescopes. So you have to study it in radio. And their study is very important because sometimes there are ejections which come out which are powerful, and it may damage our power grids, or it can also damage our spacecrafts. So some of them are studied through using the Gauri Bidanur Observatory here. And we have a south observatory to study the nighttime astronomy, basically the stars, etc. Vainabap Observatory, where we actually collect data for stars and get their spectrum and estimate what kind of elements they have. So that kind of research happens here. In Crest Hoskote, which is actually the Bangalore rural campus, we have a very unique facility, which is the Space Physics Lab. And there we integrate our space payloads, and our main station is out here. headquarters. And we also have a footprint in the sky. Basically, the UV imaging telescope on the Astrosat, which has completed 5 years in orbit, is integrated in our CREST campus, and we have our the payload operations of this particular telescope happens from here. So this is the space telescope out here. So these are our footprints, and all these studies which I mentioned, along with studies of the sun, are carried out by these things. I'll show you some pictures of these field stations as well. So this is our Hanle campus. We have a 2-meter telescope there and also 70-centimeter telescope. And this is the Hosokote campus from where you can see the dish. We remotely operate them. So if I want to use this a telescope to collect some data for a particular object, I don't have to go to Hanle, I have to go to only Hoskote, and the remote observations are carried out. And this is the Kavalur campus, South campus. You can clearly see this is more green, like you have greenery, and this is, you can see it's a barren, and this is because of the height. And these are the two telescopes which you have. This is a 2.3-meter Wind-Up telescope. It's an indigenous telescope built in 80s. And this used to be the largest telescope in India till a few years back. And now we have a bigger telescope in by Aries at Devastal. This is a 1.3-meter telescope which is erected 5 years back. And this is Astrosat, which is being put together in a clean room in ISRO. And this is the dipole array, which is there in Gauri Bidanu to study the plasma. And this is the Kodaikanal telescope. So these are the host of facilities, a collage of things put together from our field stations. Now, I also would like to study that why do you want to study the multi-wavelength view? Because you can see that you have to understand, in order to understand the full physics, you need to understand them in the entire wavelength range. Now, to give you a difference, if you look at the same galaxy in various wavelength, you are actually tracing different traces. Because if you look at a galaxy which has gas from which the stars form, and when the stars die, they actually give back the material, the polluted material back, and they also disturb the entire galaxy, and they have this X-ray remnants out here, and then they ionize the medium as well. So the dynamics, the stars forming, the stars death, and the mixing, etc., produces different physical processes, and these processes can be traced at various wavelengths, as I showed you, but these wavelengths are to be monitored from the Earth as well as from the space. So if you put together a collage of a particular galaxy, this is the molecular hydrogen, this is the atomic hydrogen, this is the ionized hydrogen. So these are the three different forms of hydrogen, which has to be traced in various different forms. We cannot trace molecular hydrogen directly. Atomic hydrogen is done at the radio wavelength, and ionized hydrogen is done in the optical wavelength. So you have to combine the wavelength to understand a physical process of just hydrogen. How is it atomic? How is it molecular? And how is it ionized? So that is the trend to see how different wavelengths are coming together to understand just the ionization of hydrogen in a galaxy. Okay. And how do the other things contribute? You have lots of molecules. How are the molecules distributed? You see it in the infrared. Then you see where these molecules come together to form new stars. Where are they? You need UV. And when they die, do you have any supernovae remnants or X-ray emitting sources, binaries, etc., black holes? You need X-ray. And then entire light for the galaxy, where are they coming from? All the stars. So you see in the optical. So let's say some 30 years, 30 decades, 3 decades or 4 decades back, or at least 5 decades back, you had only optical observation. So you could study only some aspect of it. Now, with lots of technology, which is driven by astronomy also, satellites we produce lots of these images. All these are from the space, which has been possible only in the last 3 to 4 decades. And they help us to understand how the stars form, how they where are they form, how they form, and how they die. So this is not only just about our galaxy, but if you look at outside galaxies also, stars drive the entire thing. I think I'm almost done with it. Yeah. So this is, in the case of general stars also, we understand the energy and wavelength emission. So all these data points, as I showed you here, even for a single star, we use all the wavelength ranges right from UV to infrared, using various missions. Many of them are ground, many of them are space based. So and the models. So all these put together, we are able to understand what's out there, and multi-wavelength is the key factor. Now, moving forward, where are we? So, is there anything which we still need to do? Yes, because you can see that in the last 20 years, we know much and more about the planets around stars, which was not a big thing in the previous century. Right now, the main thing in the century is that we know that most of the stars have sun-like stars have planets, and there are many solar system out there. And are there any planets which actually can harbor life, or are there life out there? So that kind of a questions are being more and more asked. And also, how do we find them out? We need, you can see that the reduction in light when a planet comes in front of a star is only 1%. And in order to detect that, you need to have much better efficiency. So it is very difficult to find a planet, and not only find a planet, you the what is out there in the surface of the planet, because there's hardly any energy emitted from there. So all that, as I said, is we are collecting the energy which is emitted by something which is not emitting anything, which we cannot detect. It is very hard to find. So you have to infer its presence. So inferring its presence and inferring certain molecules presence is difficult. So we use certain types of techniques to understand them, which means that you need to detect more light, which would mean that you need to detect more, you have more collecting area. So in a telescope or any instrument for that matter, you need to collect more energy, means you need to have bigger mirror collection. So India is partnering with other international partners for this 13-meter telescope. What it means is that the mirror out here cannot be made into one single piece, because you can't have a 13-meter single mirror. So the maximum size you can go is about a few meters. After that, the mirror breaks and you can't support it, etc. So the technology, what is now known is the multi-mirror. You make small mirrors of and different same similar shapes and similar sizes, but different surface configuration, so that you can put everything together and adjust them computer active support, so that they actually look like or act like a single mirror, which is actually very technology challenging. But that is being done with smaller number, and now we want to increase that number to 500, which is a very challenging task. And not only that, it will be, the entire thing will be looking like a football field. The size is very big. So this is a very ambitious mission, but the advantage is that you can actually study the atmospheres of all the identified exoplanets to see whether the life exists out there. And not only that, what exactly happens? Are they first stars? If the first stars are there, what is the chemistry? So these kind of questions which we cannot answer will be answered by these kind of instruments, which is being planned, and India is part of it. Now, what is India doing? India is also India is partnering in terms of contributing to certain types of making the mirrors, and the entire support assembly, which is a very challenging task, is being taken up by our scientific institutions as well as industry. And we are also providing some software for integrating the entire thing. You can see that it is like a very complex system. Everything has to talk to each other, and huge amount of information has to flow through. So all these backbones for communication are being developed here. And we are also party to certain types of science instruments which we are proposing. So that is what is being done here. And with respect to sun, we are we'll be launching the payload called the Aditya L1, which is to study the sun. And the kind of a brown box which is sitting here called the VELC is a visible emission line coronagraph, which is the biggest of the instrument in this mission, is is being built right now in our Hoskote campus, where the space science lab is there. Now, this payload, what it does is it creates an artificial corona, so you can actually always study the corona of the sun. So what is actually, we otherwise we'll study only during the total solar eclipse, because the corona is very faint. So you block the sun and make only study the corona. So that is what this thing will be doing. Now, for that, to look at the sun always, where is why, what is the L1 out here in this picture, in this title? You can see this is the sun, this is the earth, and this is the moon. Now we have something called Lagrange points, where the gravity from the sun onto if you put a point object on this line connecting the sun and the earth, there will be a point where the gravitation is getting balanced, and now that is the point called L1, Lagrange point 1, and this spacecraft will be positioned there. Now, what is the advantage? It will move with the earth along like this, but all the time it will be facing the sun. So you will have a unobstructed view of the sun all throughout its mission. And since the gravity is balanced, you don't have much of a maneuvering problem. So that is a very brilliant idea, and this is the first time we'll be sending a spacecraft to this particular point, and the IAA, our institute, is contributing to this to study the sun, the coronal properties of the sun. And not only that, from our land, we also have a proposal to make a solar telescope in near the one of the places in Leh, and the site is identified, and we have been characterizing it for the last decade or so. So we expect to put a new technology telescope out there in Hanle region to study the sun in detail. So this to study the sun, and this mission to study the coronagraph. So put together, we will have a state-of-art facility in our country, built in our country for our own people to enhance our skills and understanding of the sun. Yeah, thank you. I'll stop here.
Yeah, thanks a lot, Professor Annapurni, for an interesting and thought-provoking lecture on why should we study stars. How exciting is what we see in the sky, Milky Way, path of comet, Quasar, etc. You touched upon these things in a very interesting manner. You gave a nice analogy of stars being like live nuclear reactors, and how heavier elements are formed by hydrogen through nuclear reactions. You also gave a glimpse of different telescopes in India to study stars and the upcoming uh, infrastructure facilities, and India's contribution to the international projects. And maybe here now you can have a look at this Q&A and pick up some questions and answer to the students. And there may be a lot of questions, so rest of the questions our team will take up through email. And if we are stuck with the questions, then we'll definitely contact you.
Yeah, okay. So I'll just quickly go through some of them.
Please.
They are okay. So first question is, can we distinguish satellite and stars by looking at the sky? Means, how do we know that this is a satellite and this is a star? I think you should look at the sky. You will be able to figure it out yourself. The thing is, satellites, it's a near Earth. Basically, the satellites which reflect light onto the Earth has to be near Earth. Okay, that's about 300 to 600 kilometers. Okay, and that height, the orbital period you need to stay stable around the Earth, they have go around at least 90 minutes. Once in 90 minutes, they go through. So the speed at which they go through is they have to move faster in the sky. And stars don't move, right? I mean, you can't figure out that they're moving. You have to take off after 1 hour. You go back. Oh, their position has changed with respect to something stationary in the Earth. So they move. So you can figure that out. There's no problem. Why relative position of satellites is not enough for locating? That's also something which you should think for yourself, because the satellite could be in any part of the, just like what I'm saying, the GPS satellites go 90 in one, I think I'm not very clear about the actual time, but then it's about a couple of hours for one orbit. Now they're moving very fast. They don't know whether it is in that part of the Earth or this part of the Earth. And even if it is there, they're moving. So they have to locate at each point, they have to have their orbit absolutely precisely known. That is not possible. So that I'm saying you can roughly know, but then in order to pinpoint, you cannot say that I'm somewhere in Bangalore, right? That is not what you're looking at in GPS. You have to position it with accuracy, and that accuracy cannot be achieved. And what are wormholes? Sorry, I don't want to answer that question. I'll come back later. These are theoretical predictions for certain things. I didn't cover at that level. Can we say black holes are only present center of galaxies and nowhere else? No, not all galaxies host black holes. So only some galaxies host black holes. How can we master physics? Nobody can master physics. It's something, it's a philosophical question, so that's not possible. The best astrophysics lecture I have, okay. What explain can, no. What happens to, see, master physics is, see, physics is nothing but, I mean, in general, you inculcate a questioning approach. So physics is something, but you have to understand how it works, why it works. Okay. And you understand certain laws of physics and it has to fit. So there are certain logic, there is certain type of activity happening there. So you keep asking why it is there, what it is there. So that leads to physics within the framework of physics. So you have to read up about physics and you have to keep exploring, questioning, understanding. So that is how hand in hand it moves forward. No, it's nothing called mastering physics. What happens to the core when the stars die? Okay, the core becomes quite dense, and again, the laws of physics are applied there, and there are certain something called, we call them as compact objects. They are um, either due to Pauli's exclusion principle, they cannot be compressed further. So they are dense material. Either it could be neutrons or it could be just atoms. So it could be just, they cannot be compressed further. So they're called compact objects, and they either white dwarfs or neutron stars. But they are, I mean, physics understands what it is, why they're like that. So that is the end products. What type of star sun is in this picture? Okay, I think I don't remember what picture that is. Can we generate energy from high energy stars just like we do from true solar energy? Okay. I think there's a fundamental difference here. These stars are very bright, but they are very far away. So the energy, if you want to convert, you have to collect them first properly. Here, they are trickling down, right? So very trickling only you can get. So if you bring that star close to you, it's fine, but you will be fried. Beware, because they emit too much of energy and no life can exist nearby. So you have to, there's a balance between why we are here and how much energy sun is emitting. If we go closer, we are fried. So sun is at the right distance where we can collect energy and we can also survive. We should remember that.
I think we can say to them that in a controlled way, making this energy in on Earth is the example of the fusion reactors, as the tokamak and such kind of things. That is also mini kind of or micro kind of things what we have in the stars, trying to make in the harvest the energy. Yeah, I just wanted to say that. Yeah, yeah.
Thanks.
Yeah.
In nuclear reactor in stars, does neutrons come out of stars? They're unstable. No, they don't come out. Actually, in stars, the outer layers are actually ionized gas. So all these things happen within. There's a temperature gradation from center to surface. So all these things happen within that itself.
Professor Annapurni, I have one curiosity. This point L1, which you said, is the point where the gravity becomes zero because of the balance, the force of attraction from the sun and the earth. And putting this equipment there for watching sun and getting information is this something new, or is a new strategy, or what? It was being followed earlier also? I mean, just out of curiosity, I'm asking this.
Yeah, that's a very interesting question. Actually, it is known that we have L1, L2. So if you want to study the sun, you have to be in between sun and earth. But if you don't want, like if you want to study stars and galaxies, you don't want, right? So you want to be on the opposite side. You also have a similar position, the sun, earth, and then away. That is called L2.
Mm.
So many spacecrafts are already there in L2,
Okay.
which study uh, the dark sky.
Okay. So L2 is
Because
on the other side. Yeah.
other side, yeah.
Okay.
These are known, theoretically known, and I think L1 some spacecrafts are already been there, but it's a capability, it's a quite a far distance and communication with respect to that positioning. India has not done it, so it's a technological feat.
Yeah. So
So
this.
other some countries have done it, like I think NASA and ESA, both of them have done it. The European Science Agency and the US Science Agency,
Yeah.
Space Agency, sorry. But Indian Space Agency has not done it. Maybe Japanese have also done it. Yeah,
So
but it's time for it.
the temperature also must be quite high there. So what is the typical temperature at L1?
No, temperature is not high.
Not high. Okay.
No, no, no. That's we are not that close to the sun that it is. Yeah,
Yeah. Yeah, it is more close to the Earth because Earth is a smaller
yeah.
than Sun. Yeah, okay.
Yes.
All right. So I think I know there will be a lot of questions therein. So if you agree, then we can take up those questions later through email. Yeah.
Yeah.
Yeah. And so I take this opportunity to thank you once again. And you see, this is at my background, the beautiful campus of University of Petroleum and Energy Studies.
Yes, it is
And
beautiful. Really beautiful.
I would like that you visit sometime here, and students will be curious to talk to you and discuss with you. And we have one program which is the Shakti program, where actually we invite or online or face-to-face meetings to motivate the female students. The Shakti name comes from the Durga and all in different fields. So you are also kind of Shakti in knowledge in this astronomy and this thing. So it will be very interesting for the students and for us if you visit sometime in future whenever pandemic is over. So that is my invitation for in future, ever standing invitation. So now let me thank my colleagues, panel members, Dr. Rajiv, Dr. Sarath Lal, and Dr. Parasajit. And I would also like to thank person behind managing the webinar, Mr. Siddharth. And students are also requested to fill up the feedback form, and they also can actually go through. We will contact them for quiz program. All those who have registered in different quizzes, we'll send the mails, and they can get registered freshly for the quiz. So Siddharth, can you display certain things for the student? The feedback form and the about the quiz. Siddharth, okay, yeah. So students are advised or suggested or requested that please fill up this uh, small feedback. And I think there is one more display for the quiz where all of you should get registered. Yes. So Siddharth, you should remove this uh, feedback form. Then only the student will be able to see. So feedback form is actually okay. Now it's correct. Yeah, yeah. So all the students and teachers will see you on 7th of August at 10 a.m. But you need to register for this, which is of course free registration to participate in this. Okay. So have a good time, stay safe, stay healthy, and goodbye to Professor Annapurni.
Yeah, thank you. Thank you for.
Namaskar. Thank you.
Bye.